In this video, we will obtain the condition for balance in Wheatstone's bridge. And important applications of Kirchhoff's law is Wheatstone's bridge. We have two Kirchhoff's law. One is called Kirchhoff's current law, other one is the Kirchhoff's voltage law. These two Kirchhoff's law will help us to get the condition in Wheatstone's bridge, or a condition for balance in Wheatstone's bridge. What is the benefit in studying Wheatstone's bridge? Wheatstone's bridge is highly helpful in determining an unknown resistance in any electrical network, and it is used to compare any two resistances. Next, let us draw the Wheatstone's bridge circuit and describe it. Here, the Wheatstone's bridge is constructed using 4 resistors and they are connected like this in a diagonal form, and this resistor is named as P, and this is Q, and this is R, and this is S. This junction is named as A, this junction is named as B, this is C and D. And between these junctions A and C, a battery is connected. And between this junction B and D, a galvanometer G is connected. This arm between A and C is called as battery arm, and the arm between this B and D is called as the galvanometer arm. When a current of I amperes reaches this junction A, it branches out as I1, and here it is I2, and when it crosses this junction, it goes as I3, and here it goes as I4. Again, when it comes out of this junction, it is I. This arrow mark is very important. See, this I1 current is approaching B, and I2 current is also approaching D, and I3 is approaching C, and I4 is also approaching C. Finally, the same I amount of the current comes out of this junction. So drawing this, the direction of the arrow marks, that is the current, is very important in this circuit. And the galvanometer has the resistance of G, and the current through this galvanometer is taken as Ig. Okay, now we have a junction at B and a junction at D. Now let us apply Kirchhoff's current law. Kirchhoff's current law to junction B. See, at junction B, I1 current is approaching, I3 current is leaving, and Ig current is also leaving. If a current, okay, what is Kirchhoff's current law? The sum of the current meeting at a junction is equal to 0. So the total current meeting at the junction B will be equal to 0, and the current which is approaching will have a positive sign. The current which is leaving the junction will have a negative sign. See, at junction B, the I1 current is approaching, so it is I1, and the current Ig is leaving, so it is minus Ig, and the current I3 is also leaving, so it is I3. This is equal to 0. Let me take it as equation number 1. Then look at junction D. So at junction D, we could see the I2 current is approaching junction D, IG is approaching junction D, and I4 is leaving the junction. So it is I2 plus IG minus I4, because I4 is leaving the junction, will be equal to 0. Let us take it as equation number 2. Then let us apply Kirchhoff's voltage law. Kirchhoff's voltage law. So Kirchhoff's voltage law is applied for a current loop. So here the first loop taken is A, B, D and A. So for the closed loop, A, B, D, A. So what is Kirchhoff's voltage law? The sum of product of the current and the resistance for a closed loop will be equal to the EMF of the loop. So the EMF of the loop is equal to 0, and the sum of the current and the resistance. What is the current here? I1 P. Again this is plus IG G, and this one is leaving the junction, so it is minus I2 R will be equal to 0. Let us take it as equation number 3. Then we will apply the Kirchhoff's voltage law to the closed loop A, B, C, D, A. That means for this entire loop A, B, C, D, A. So when you apply, so what is the current into resistance there? It is I1P. Again this is plus I3Q, but this I4 and I2 are in opposite direction, so it is minus I4S minus I2 are equal to 0. So I1 and I3 are in positive direction, or they are going in one direction, or I2 and I4 are going in the other direction, so it is minus sign here. So this is equation 4. Okay. Now let us assume this galvanometer G has no internal resistance. G has no internal resistance. At balanced condition, these points B and D will be at same potential. This B and D will be at the same potential, so that no current is passed through this galvanometer. As I was mentioning, at balance, the points B and D will be at same potential, then no current flows through the galvanometer G, so IG will be equal to 0. See, look at equation 1. So if I put IG equal to 0, we will get, so this is equation 1, I1 minus IG minus I3 equal to 0. At balance condition, IG is equal to 0. Substituting in this, we get I1 minus I3 is equal to 0, which tells us I1 is equal to I3. The current flowing in the arm A to B will be equal to the current flowing between the arm B and C. In the same way, our second equation is I2 plus Ig minus I4 equal to 0. Again substituting the current through the galvanometer Ig is equal to 0. This becomes 0. Then we get I2 minus I4 equal to 0. Taking this I4 to the other side, we have I2 is equal to I4. And this is our third equation. I1P plus IgG minus I2R equal to 0. Again this Ig will be equal to 0. So we get I1P, and we have also shown that I2 is equal to I4. I2 is equal to I4. So we get from third equation, it is I1P plus IgG minus I2R equal to 0. And this Ig value is equal to 0. So this entire term goes to 0. So we get I1P minus I2R equal to 0. Or we can write I1P is equal to I2R. This is our fourth equation. I1P plus I3Q minus I4S minus I2R is equal to 0. Now, in place of this I3, we can substitute I1 because we have shown this I1 is equal to I3. If I substitute, I will get I1P plus I1Q. In place of I3, I am substituting I1 minus. And we have also shown that this I2 is equal to I4. So in place of I4, I can substitute I2S minus I2R equal to 0. See, here also I1, here also I1. So I can club these two terms, or I can take this I1 out, and I will have P plus Q minus this, taking this I2 outside, we have S plus R is equal to 0. So this minus term can be taken to the other side. So we will get I1 P plus Q is equal to I2 S plus R. So let us take it as equation 5. This as equation 6. Now let us divide equation 6 by 5. So we have to divide this equation 6 by 5. If we divide, we will get I1 into P plus Q, the whole divided by I1P. On the other side, we will have I2 S plus R divided by I2 R. So this I1, I2 will get cancelled. So we will have P plus Q by P is equal to S plus R by R. So if I divide by P, I will get P by P plus Q by P is equal to S by R plus R by R. So this is nothing but 1 plus Q by P is equal to S by R plus 1. So this one and this one will get cancelled. So we have Q by P is equal to S by R. Taking the reciprocal of this, we get P by Q is equal to R by S. This is the condition for balance in Wheatstone's network. P by Q is equal to R. P by Q is equal to R by S.